Welcome to the stream. We're going to see how this goes. Today we are working on super simple neural network. My volume's worked out. Make sure everything's working. How's everybody doing today? Amazing. So good. So amazingly good. Yep. Yeah, things are happy. So I got started. I cheated. I started the code a little bit. And let me turn my volume down. So the code I have up on GitHub. There it is on screen. So I haven't really done too much at all. I have a whopping 2 commits, and I really don't have much code in there yet. We'll look through it real quickly. But what I started doing and what I want to finish or get into a moderately good place by the end of the evening is a ridiculously, foolishly simple neural network. That's the goal. We're not doing any optimization, not doing any matrices, any crazy math, ideally. It's going to be simple. We're going to see how far we get. The tutorial I'm using is right here. It's in the description. He maths a little bit in here. So we got, yeah, we're gonna see how we do with the math, because it's been a while since I've calculus, and it's been an even longer time since I've tried to do that inside of code. But we're gonna do the best we can. And anyway, we're just gonna see how we do. So what I have so far is, let me show you the code that I have so far. Let me get the text a little bit larger for you. Right, so I made a simple neuron class, and then I literally am connecting up. I'm building each neuron here, and then I'm connecting the neurons here, and then I just do a very simple forward pass, like one calculation's worth, and I'm validating that the output matches the guy's input from the tutorial. So what we're doing is we're taking this graph right here and we're putting it into code, and then we're gonna hopefully complete the tutorial and take what he does on paper and put it into Objective-C as just a very simple neural network. And I will ask in advance for your patience, because this is the first time I've tried to do this. So I've done this part. So I built this graph here of weights and neurons. I have the input neuron, hidden layer, and the output layer. I have all of that. I have the bias set up. I have pre-filled it with these values. These are effectively random. He just chose them for no reason. And then here, we want, given these inputs, we want it to create these outputs. The very first thing is I've started working on this forward pass, and so that's the next thing that we're going to work on, is finishing that forward pass step to see how we do. So I've calculated this right here to get this output. This is that an image? Is that really an image? Yeah, man, that's ridiculous. But fair enough. So I've gotten 0.3775, and so we will run it on the simulator and verify that we are getting. Where's the simulator? Yeah, it's just taking a while to boot up. Let's try again. So now we get, there we go. There it is, right? So we spat out the correct value so far. So now we're going to continue our work. This is that first step. He calculates the net input, is what he talks about. So here we calculate our total net input for H1. So net of H1 is equal to this value. And then we squash it using the logistic function to get the output of H1, right? So then our output is, we have calculate net, so this is CG float. We call it net input. And output is equal to self squash the net input, right? And so then the squash function here, oops, right? Pretty good. And so then we want the output to be, our goal, our target is this 0.59 business, right? So we have turn divided by some stuff. E, I believe is that. E to the negative net input, right? Yeah. I think that's right. Let's just see what we do. I can't remember if that's the correct function. I feel like it is, but we'll find out. And so now when we run it, let's see what we get. Kamok, how you doing, man? Live coding support, always good to see you. Look at that, 0.59327. I think we did it. 0.59326992, right? And so that means we're getting some rounding error on these floats, I believe. Right? Is that what it means? Get this out of the way. Go. Oh no, it's just rounding in the printf. So yeah, we got that. I was going to say that should not be rounding error already. So 69925, blah, 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 right? We did it. So carrying on for the same process for H2, we should get some other value. So let's go here in our view. So if we do a forward pass for H2, and it is the same. Or it's almost the same. 59688 instead of 5932. 5932, 5932. There we go. Look at us outputting the correct thing. Awesome. I'm good, man. I'm doing really good. Thanks for asking. Yeah, we got the correct answers. Awesome. Yeah, I'm legitimately excited because I've been wanting to play with neural network stuff for a very long time. And I feel like I have a moderate understanding of what is happening, of what the process is, but I do really well when I can look at the very smallest pieces and kind of poke at the numbers and watch how the numbers flow through a formula or through an algorithm. And so that's my goal today, is to make like just the stupidest, just the really simplest network possible at all. And so we just finished this. And then that way, once we get just the simplest version, then we can start playing with it and kind of poking at it and seeing what we're doing. Got my volume just a little bit. Just a wee bit. How are you guys doing? You guys doing good? It's 12:37. GMT's 5 hours ahead, so it's 5:37. So if you're in Europe, you're waking up early. If you're in the States, you're staying up late, like ridiculously late. Pretty awesome. Okay, so now we repeat this process for the output layer neurons using the output from the hidden layer. So here's the output for O1. Now we should be able to, we're calling this in order, right? So we do a forward pass there and a forward pass there. O1 and O2, forward pass. And O1 and O2. O1 and O2. Okay. So what I'm expecting to happen is this, we already know works. This should just happen because every time a neuron, here's how the neuron works. I should explain this. All right. So a neuron has a bunch of weights and an output that it saves, and it also has a bias, right? Student programmer, how you doing, man? And so then we add a couple inputs. We set the bias of the neuron. We add a couple inputs to the neuron, right? I'm going to move this guy down here so they're in chronological order. We then do a forward pass, which is going to calculate the net input and then squash that net input using our nonlinear formula. Saves that as its output for that round. And then after that round, that's just what it's going to use as its output, right? And here's some helper functions that we just did from that paper, or from that blog post. A static neuron is a lot easier. It's just a static value, and then that's it. Nobody cares about it after that. It doesn't calculate anything. It's just a number, which makes it really easy for inputs and outputs. So that means our input is just a value, our bias for now, just a value, and our hidden layer and our output layer are proper neurons, right? With weights and the whole bit. And so the hidden layer is set up as inputs to the two inputs, and the output, its inputs, is that hidden layer, right? And so then that lets all of these objects right here, we have our bias right there, we have our inputs, we have our hidden layer, and then we have our output layer. Those all are connected to and matched up with this diagram. So they're all connected exactly like that. Which means when we run this, we should, here's the output for O1 and O2, we should get those values. O1 is 0.75 and O2 is 0.77. Are we going to do it? What do we think? Something's wrong. Something's wrong. So output number one. Super and doing good. Hope you're having fun with your neural net project. I think neural nets are cool, although I don't really understand them. Well, perfect, man. This is a perfect stream because I don't understand them either. That's what we're trying to figure out. We're trying to make the simplest possible neural network, and that way we have code that accomplishes the task and then lets us kind of poke at the numbers and we can debug and watch the numbers happen. That's what we want, which is perfect because our outputs 0.75 and 0.65 are different from 0.75 and 0.77. So 0.7513, so this guy feels good, but O2 is wrong. So O2 I wired up wrong, apparently. So O1 has bias, but O2, there we go, that's what I want. O2 did not have the bias set up, and so now I think, now are we okay? Yep, now we're okay. That was great. Big boom. What's up, man? Welcome to the stream. That means we have, now we're doing so good. Look at us, we did the whole forward pass just now. Nerding out so hard. Okay, calculating the total error. So we can now calculate the error for each output neuron using the squared error function. Sum them to get the total error. Okay, fair enough. So what we want is the target output for O1 is 0.01, just because they've defined that way for no reason. The neural output this, and therefore its error in the process. Okay, so that means we can do an error per neuron, which I feel good about. error given target, right? Target value. And so then that formula was 1/2 of target minus output squared, right? Of target minus output, and that's squared. Is that a nasty way to do target minus output? Probably is. That's how we're going to do it. If, right? We'll clean it up ever so gently. Right? Now we have an error given a target value. There we go. And then that means we now have error. Oh, come on. Didn't I just? Yeah, I did, but it needs a compile. Error given target is 0.01. Wasn't that what he wants? Yeah, 0.01 and then 0.99 are the two targets that he arbitrarily decided. Right, and then E2. So E1 and E2, E1, E2, awesome. So that should, I think, give us the correct error values. And so then E total is just their sum. Not super exciting. E error total, right? E1 plus E2. And we'll go ahead and output that too, just for fun. Right? Now when we run that, we should get the correct error values. Feels right. 0.27, 0.29, right? Sorry, 0.27 and 0.023. So E2 is wrong. Is that what we're saying? Target is 0.99. I probably did that wrong. 0.99 because I typed it in wrong. There we go. Great. We have an error of 0.27 and an error of 0.02, and then we have our E total is 0.29. I'm going to move this guy down here. There we go. All right, so now we have all of our error business has been calculated. Now the back pass, this back propagation was what I was most curious about. So this is the part that I understand in concept, but don't understand kind of in math necessarily. This is good. So output layer, consider W5. So I'm actually going to pull up another tab so we can have this open as well. Here, I'll just do this actually. There we go. Right. There's our network. It says consider W5. Right. We want to know how much a change in W5 affects the total, the error total. Right. So he's talking about this guy right here. So if this guy, his error is 0.25, so he has a sizable error. And how much does this weight versus this weight right here affect that output? That's what we're going for. So E total given dW5 is the partial derivative of E total with respect to W5. And I'll say the gradient with respect to W5, right? So that makes sense. Then by applying the chain rule, you know that the D total to D out of O1, the D out to d net of O1 and d net to W5. Okay. And then he's mathing a lot of things. That's fine. We need to figure out each piece of that. So E total we have. So E total of E out, right? So he takes the derivative of this with regards to this variable. Fair enough. Yep. So that drops the 2 down. Which, yep, 2 minus 1. I get it. That drops the 2 down. Here, let me. Oh yeah, because it's just of that variable. Okay, I'm gonna get some. Yeah, I am. I'm gonna get some pen and paper so we can do this by hand. Just a second. All right, here we go. This is where I find out how bad the stream lags behind me. And unfortunately, I got to use. Unfortunately, I don't have enough microphones, or I don't have enough USB ports, so I can unplug my microphone. Apologies if that was loud. It's probably not. I'm using a less awesome microphone. It'd be interesting to see what the quality is, actually. Oh, it's actually the same. It's adorable. I had my microphone plugged in, and it was not set up to use on OBS. Oops. That is awesome. Okay, that's fine. Okay, this will be good. This way we have paper and we can actually do the math. Quick time player. How many of y'all have calculus? Y'all feel good about it? It's been a long time since I have calculus. We're going to see how much I remember. Hello, face. iPad 2, iPad Pro. All right, so now we got it going. Okay, now we can math. Do it. Totally do it. Okay, so what he's got is, can y'all see that okay? Can y'all see that? Hopefully you can. So if E total is equal to 1/2 of target O1 minus out of O1 squared plus 1/2 target O2 minus output O2 squared, right? And so, now what we want to do is we want to take the derivative of dO of O1, right? Of ET, of E total. And so that's going to take this guy and drop him down. And this guy, we're taking the derivative of O1. So this entire term doesn't have an O1 in it, so it's just going to go away. And so that's going to be the same as if we took the derivative of just this, right? That's the only thing we care about. And so then that means this guy drops down 2 times 1/2 T01 minus O01 and 2 minus 1, which is just 1, right? And this is just 1, right? So it's just, but he gets a -1. Where does he get the -1 from? Am I remembering things wrong? Why do we flip the sign there? I'm going to believe the man. Professor, how's it going? I'm doing good, man. Cybercomic, how are you? Glad to have you on the stream. Do you remember calculus? There's 12 people here. That's live coding, and one of you remembers calculus. 2 times -1/2. Is it? I don't know. The original formula was +1/2 here, right? You're studying. 2 minus 1. Yeah, it's 2 minus 1 in the exponent, right? Right there. Akashikara, I hope I pronounced your name moderately correct. Yeah, no, it's a good suggestion. I mean, it's something. It's derivative, cheat sheet, right? I did not even spell derivative even close to correctly. The power rule, yeah, so this is what I was doing right here, this power rule. Where is he getting the, where is he flipping the sign? Am I crazy? I mean, I'm going to believe him. I'm going to code it however he wants me to code it. But I don't understand why that. Oh, I think it's because of gosh, what is it? It's going to be in here, and then we're all going to remember what's going on. I think what it is so if you have ddx of foo equals, can y'all see that over there? 3 minus x squared, right? What this is going to be is this is going to be 2 times 3 minus x to the 2 minus 1. But then you also have to take the derivative of this thing inside of here, right, with respect to x. And that is going to be -1, right? Because ddx of negative x is -1. And so that, I think, is where that -1 came from. But I can't exactly remember that rule. And I'm just going to pretend that that is the answer. And I'm pretty sure that's the answer. I'm probably staring at it on this piece of paper. I think it's this, yeah, this guy right here, right? Yeah, so anyway, he just said it. He just said the chain rule. So if we want to take ddx of f of g of x, which is, in our case, f would be 1/2 of some thing right here squared, and then g would be some constant. I don't want to use d there. Let's use y minus x, right? And so then f of g would be 1/2 y minus x squared. And so that means d dx of that would be the derivative of this guy times the derivative of this guy, right? Hopefully that made sense. I feel pretty good about it. So that means, let's get back to our tutorial. So now we understand where that derivative came from, which is nice. So we have, so we need to calculate. So how are we going to put this into a method? We just want to say, so this is derivative out versus derivative target. So do we need to, I don't think we need to put that in, yeah, that's fine. Error given target have, and so we want the error given error total, right? It's e total, that's derivative of e total. So yeah, so we don't actually want to do it inside the neuron. We want to do it, we're just going to do it outside for now, and we'll clean it up later. So d error of O1, right, is, we're going to say negative, and that's, oh, that's just going to be out minus target, right? Is O1 minus 0.01, right? So we'll do cfloat O1 target, clean that up. Awesome, this will be O2 target. O2 target, right? Pretty good. That means we're only going to calculate it for error 1 right now. Should have used NumPy. Yeah, so the reason I'm doing it this way, I totally agree with you. So if you want to do this for real, you should use Python and NumPy and SciPy and all that kind of stuff. I am most comfortable in Objective-C, and I just want to make it really dumb. I don't want to make it efficient. I just want to understand what's happening and how the numbers are flowing through it. If I wanted to do it for real, I think Python would be a good way to go, and then I could use all of its matrix and optimizations, and it would be really, really efficient. I just want to make a really dumb one, but you're absolutely right. You're absolutely right. That's definitely a better, kind of more correct way to go. So now, how much does O1 change with respect to its total input? So here's our other derivative, our out of O1, D1 given net of O1. Right, so here, oh, that's a simulator. I don't want the simulator. I want the iPad. So he's saying that if out of O1 is equal to 1 over 1 plus e to the minus net for O1, right? So then d, oops, d out of O1 to the net of O1, right, is going to be out of O1, 1 minus out of O1, right? And I believe him, but it's been a long time since I've derived any of that kind of stuff. But I will believe him. It's probably on my little math cheat sheet here somewhere. Yeah. d to the x 1 over x. Yeah. Oh, that's why, because it's yep. So the reason is because this function right here is really 1 plus e to the negative net of O1 to the negative 1, right? And so then that brings this guy down to the front. And anyway, yep. So I'm happier now that I moderately understand it instead of completely don't understand it. But that's fine. So let's go to d of error O1. O1 forward pass. What I want to do actually is I want to back prop given target, right? And then because here we have error 1, error total. So this is going to be, let's rename this to find the, right? I think that's what we want. And so then we would say O1 with back prop given target would be O1 target, right? That's basically what we're doing. And so now inside of here, we just did this, which should get us that value, the 0.74. Right? Elgin, good to see you again, man. Welcome. Yeah, so our error total is 0.74 for that neuron, which is fine. And so now we want to figure it out with respect to our net output. So we're undoing we're taking the derivative through the nonlinear formula, right? Which is going to be out of O1 times out of O1 times 1 minus out of O1, right? So CG float as D, what was we going to call this? D net. The out versus net, right, is going to be self latest output times 1 minus latest self latest output, right? Pretty good. And that guy is going to be what? Going to be error d net. What we'll call that. My variable names are pretty horrendous, but I think we're on target. So 0.18 is what he said. Is that right? Yep, 0.18. Yep, so our numbers are matching there. Then finally, how much does it respect to weight number 5? And so then here we can actually calculate for all of our weights, ideally. So we will do that real quickly. I less than weights. There we go. So now we're calculating for each one of our weights, which for our case This guy has 2 coming into it. First one here, weight 5 and 6. So it's going to loop over both of those, and we're going to calculate both of these things twice, right? In his example, he does it for one edge, and then he'll do it again for the second edge, but we're just going to reuse those anyway, right? So, yep, so here's our net formula, right, which is right there. And then he takes that with respect to W5, which is just going to be out of H1, right? Yeah, so just its output of H1. So output of H1 is what? Calculate net input. So his H1 was this guy's output during our calculation, which means we need to save that. So inputs, input values, right? Right? And so then when we actually calculate the net here, float, and then here, we save that value, and then we use it. And so this will actually be input. This is going to be input value. I'll call it input output. I mean, but that's even more embarrassing. Right? And so now this guy right here has yeah, so this guy right here is going to have an array of all of the inputs that we ever got, which means our derivative here, our d out to d net, right, is equal to sorry, just the d net d input, yeah, is equal to just the guy's previous output, right? That feel good? Edgar, good to see you. Thanks for hopping on. Now this guy, that's his derivative, which feels good. We just did this, so this should be 0.59. Oops. Right, and then when we run that, yep. So for each one of those is 0.5932. 0.5932. So then putting it all together, he just multiplies those 3 numbers, right? And so this is going to be d total to d input equal to d air total times d out net times d net d input, right? So we want, we're going to call this d total d net. So d total d out. Okay. And this is going to be d out d net, and then d net d input, right? D net d input. That way I'm at least kind of like using, That way when you say it out loud, that's fine. That's fine. All right, so that's our total problem for the for that guy right here. Awesome. And that we think is going to be 0.08, right? That's what we want it to be. Checking our work. Yep, 0.0826. 0.08 0.08216, and ours is 66. A little discouraging, but maybe not too bad. Oh yeah, no, that's because that's for the second one. Sorry, because I needed this guy right there. So I was looking at the wrong number. So we did do good because it's right here, 0.082167. Yeah, so we did good. We are correct. Awesome. So now we have all of that I like. You also see this calculation combined in the form of the delta rule. So d total, yep, so they just smashed it all into one formula. That's fine. Alternatively, we have the first two. I almost wish you would like color code these, right? Because that'd be really handy for me. The node delta. Yeah, that makes sense. That makes a lot of sense. Yeah, so because it's basically saying this little blue box, it's saying since these two terms are the same, right? Node delta, right? Rather delta node, I think is the way that would be said. Yeah. Is equal to those first two right here, right? And that's just a convenience for paper writing, whatever. Some sources extract the negative sign. That's fine. So to decrease error, we then subtract this value from the current weight, optionally multiplied by some learning rate. We'll set to 0.5. So if we had a so that means we need to swap out the weights. Oops, sorry, in this array. Oh, actually, we don't use the weights at all here, so we can do that. Oh, yeah, we do. Just dummy. Updated weights. Updated weights times right? The total D input. I like that. I think that's correct. Now we've updated our weights, which is the hard part. Theory. So then we can repeat the process to get the new weights for W6, W7, and W8. Yeah, so W6, W7, W8. So then that redoes all of those, and then that's helpful. Yeah, so then what we can do here, so O1 and O2, is O2 target, right? And so one thing that I would like to do is look at our weights like that on the neuron. There we go. And so then this way we can weights after back prop. Let's do all of them like that, right? So there's our 4 weights. And so then now let's go here. I can kill all of these logs because I don't need them. Right? And what we are going to do, no, we're not going to do that. That's fine. So now what we should see is we should see these values, the 0.35, 0.40, 0.51, and 0.56 when we run this. Right? What did we say? I don't think that's right. It would have been 0.35, 0.4, 0.51, 0.56. But that's not what we're getting. Why is that not what we're getting? He says after he restores all of his stuff. Right? That's only back prop number 1, and let's only care about his weight. All right, so, oh, that's why, because he had the learning rate. Yeah. Okay. So we'll do this. We'll make it a class method, cgfloat learning rate. That's fine. So then here, our updated weight is going to be neuron learning weight times, oops, sorry, I was in the wrong place. Here we go. Now we should have the correct business, right? Noobs, how you doing? 0.35 and 0.40, that sure feels right. 0.35 and 0.40, so now if we add back in that business, we should get all of them correct, which would be amazing, right? Now we have 0.40, 0.51, and 0.56. We did it. Now we have all that, so let's commit that real quick. First back from output to hidden layer, right? So if you're following along on the code, I just pushed that code up. The code is in the repository, so you can look in the comments and stuff, which is pretty great. Right? It looks like did my stream die? Like my stream might have died. Sorry about that. But welcome back, just the same. All right, so now we'll continue the back pass by calculating new values for W1, 2, 3, and 4. Yeah, so at this point we have we've backpropagated, we've created new weights for these things. And so now we need to send new business and calculate it again for this one. All right. So this one's going to be interesting because here we had a one target value, right, to generate the output. But here we have two target values coming in, right? We have this guy coming in and this guy coming in. So we're going to have two inputs coming in that we're going to need to work the business on. Big picture, here's what we need to figure out. Yep, so the D total to DH1. Yep. DH1, yep, that's fine. So it's the same idea. Okay, and then this term, this first term, is expanded out to a sum of the other guy's terms, right? The sum of its inputs, which makes sense. So that means one thing I want to do here before we go any further, input neurons, and I want to do output neurons here. And output neurons are going to be the guys that we send our stuff to. So, or rather that eat our stuff, right? Well, that's I don't want to do that quite yet. All right, so looks like the stream has died. Internet is up. A good sign. Figure out if things are still up. Yeah, my server's doing okay. That's the guy that's actually doing the streaming. Okay, student, you can see it. Okay, cool. Maybe it's my internet. I don't know. Like this happens every time I stream. It kind of goes in and out. Anyway, apologies, all the same. So here we go. So we know that out H1 affects both out O2 and out of O1 and out of O2. Therefore, DE total to D out needs to take into consideration the effect on both output neurons, right? So let's just do this business right here. So starting here, right? So D output 1, that D out of H1. So the output of everything in the world with regards to the output of just this guy is equal to the output of everything in the world to the net and the net to the output, right? Okay, so we can calculate E of O1 to E net of O1 using values we calculated earlier. So this is D EO1 to D out O1. So error total, is that what he's using? 7413, yep. And then D out to D net is that. So error D net, where's he? Right? All right, so that means okay, fine. So, and that's our delta node, right? Yeah, so that's the delta, right? Yeah. Yeah. So this is delta node, right? Sounds like a totally awesome band name. Right? And so now that way this guy is accessible to, actually what we can do is make that a property. A little bit easier. Right? Now he's available to anything that used it, which is good. That means this node that we're calculating for, we're back propagating on this hidden node. So he needs to know who he outputs to, right? And so we do need to track that, right? Output neurons. Um, anyway, that's fine. So now we're going to do a add output. Oops. There we go. So then we can have right, because if this guy is our input, then we're its output, and so we need to tell it that we're its output, right? That's the idea. And so then that way it knows who its outputs are. So then here in back propagation, as we're so this probably needs to be yeah, I'm not sure. Not entirely sure. Yeah. Okay, anyway, so we can use this that we calculated earlier. And then we need to calculate that. is just a weight of 5, the weight of this guy. Oh, times his own weight. Okay, okay, okay. Yeah. So that. I'm trying to figure out I'm actually going one step farther and trying to figure out what the next step will be. Let's just go through this. So this has been a good exercise. All right, so now given target. This is wrong. So this is worded wrong. This is part of my problem. This is really my issue. Backprop given target, right? So the target is, I think I need to do backprop given delta node, I think, right? I want the other one. I want, oops, I want this, I want this one. So we have weights, and then we can actually have, it looks like I'm going to need old weights. Right? Because this is using a 0.4, it's not using the updated weight. It's using the old weight right here, right? So I need to keep it hanging around. Yeah, so that's my problem. This delta node not exist here. That's the wrong place for it. So that delta node right here should be there, given delta node, right? And then backprop given delta node, and then here yeah. Yep. There we go. So now I should have these, right? 0.35. Yeah. 1, 2, yeah. Oh, no, because this, I was wrong again, because this delta happens for every single one. So I was wrong. It is going to be better to put it back in here. There we go. And so that way it has it. Yep. And so I'm going to do a second one because this one I feel like is a special case. That's a little awkward. I want to do a different one. This is going to be a back prop given output, right? And this I just want to be called back prop, right? I think that'll be better because this method will be used for this layer, right, where it has a defined target output, feeding in the target output, and then this other back propagation will be used where it has to talk to a bunch of different people. That's going to be good enough for now, and we can probably eventually refactor this to do what this is doing, and I'll just need to wire up its output neurons in air quotes correctly, but that'll be okay. So now we can do H1 back prop through that method, and it's going to look at its output neurons, right? Yeah, to do that. So what I want to do here is H1 is just going to do a back prop, right? Neuron, yep, and just back prop, yep. Right? Now inside of here, we can actually start doing, this is weight 5, 6, yep, so now the hidden layer. So now we're going to start doing this the right way. So we're going to for 0, I is less than outputs, neurons count plus, right? We're going to do it once for each neuron, for output neuron. Yeah, so this is the one we calculated earlier. So this is the 0.13. Let's confirm that that's what we have. Yep, delta node 0.13, right? Delta out. Excuse me. Local declaration of output hides instance variable. Yep. Out neuron. Neuron. Okay, cool. Right? Now we get rid of those build warnings. Now we're good people. Really good people. Okay, so yes, we did. We just reused those that we calculated earlier. And this is equal to weight 5, right? So out weight is equal to out neuron weight for neuron self. Right? I feel like that's a better way to do it, potentially. Nope, that's a really terrible way to do it. Really, really terrible. So latest output. Wait for neuron. Waits. Object at index. Input neurons. Index of object. Neuron. There we go. Right. This is going to die a terrible death if neuron does not exist, and that's probably completely okay with me because I'd rather have that bug. I'd rather know, right? Web dev, Padata Pullman, maybe, and Jojohan, welcome to the stream. Thank you all for hanging out. Wait, right? That is outweight. So that should be, we should see a 0.13 and then a 0.4 if we're very, very good people. So this is actually going to be previous weights, old weights. That's what it is, old weights. Right? Because it's actually going to be giving us the new adjusted weight, and that's not what we want. We want the old previous weight. Right? There we go. Now we got our previous weight. Feels really good. So now we plug them in, get them together. So that is going to get, we multiply them together, we get D error to D out of H1. Oh, yep. So it calculates the error for both of those. Therefore, E total to D out total. So now that's what we're figuring out. We're figuring out D error total to D out, right? This is plus equals delta output times outweight, right? Now that should be this value right now. We're looking at these first two rows, right? We're looking at that very first calculation. So that needs to be, what did we decide? Negative 0.019, right? That's what we're looking for right there. That's 0.019. Bad for business. Bad for business. So what am I doing wrong? I have 0.13. Oh, yeah. So, yeah, 0.138. That's 0.4 is 0.05. Same process. Yeah. I get 0.05. Second time, I get 0.03. Oh, no. The second time, I get negative 0.01. And then afterwards, I get 0.03. and my negative sign is incorrect here. No, that's not the only thing that's incorrect. It's just incorrect all the way around. All right, so let's do the error out to D out. Let's verify that we're getting what we think we should here. Right. Try to actually output the correct value. And now we have 0.05. Yep, 0.055399. Yep. And same process, we get 0.03 6535. Yep. I'm looking at this value here, and wait, what am I looking at? Here we go. So the other thing that we can do is, that'll make life a little bit easier. Is we will init with name. That's going to make life just a little bit easier. That way our log files will be a lot prettier. Name. There we go. And then we will synthesize name. Name equals name, creatively enough. Yep. Right. Pretty good. And now we also want to do this, so we know that it's dead. There we go. And then here, init with name 01 and init with name 02, right? And now inside of our neuron class, we can start talking about what neuron we're actually dealing with. For this, right? This I like. This will be better, right? Now we're back prop. Oh, I didn't add the most important part. neuron. On now. So there we go. So now we're doing backpropagation for H1. So the first guy's output is 0.05, second guy's output is 0.01, right? And now, and then our total is 0.35635, 0.3635. Is that what I? Yeah, 3635. Okay, great. Yeah, so now we're correct. After all that business, we're doing it right. So now we have DE total to D out. So we just calculated this guy. We need to figure out this guy and this guy for each weight. So now I think we have this, and so this is going to be what we just did, right? So now we can self backprop given target output, which is D air total out. I believe that's going to be magic if that's all it is, and I'm pretty sure that's all it is. In H1, here total, so then we can now update W1. So now W1 is going to be this, right? So let's go here. Yeah, H1 weights. So yeah, let's just see what happens. Let's just run it. I don't think anything could go wrong. Nothing could go wrong. So this is what it thinks its new weight is. 0.149780. A little bit different than I wanted it to be. 9.3. So it's acting like I got something wrong, which means I got something wrong. So we should be seeing this guy, this 0.24, each weight. So our error, our total error out is this guy, right? And then we can do nslog for with right. That'll give us a little bit better logs to see what's going on, so that way we can validate what's happening, right? So we want to do backprop given output with 0.3635 versus 0.59327. I believe 59327. Yep, times 1 minus 53297. 0.22413. So we got the 0.2413. Good. So we calculate the partial derivative of the total net to H1 with respect to W1. And that is going to be 0.05, which we got. Right? So then putting it all together, we get this. This is a little bit different here, I think. We have total. So it's actually this d total, that's this, right? What we actually want to do, we want to cut this step out, right? So given output, so we want to do backprop given given that. Right? Then we take this guy right here, that. And then same business here. I think that's what we want. I think that's what we want. Yeah, 97, 995, 2497, 2995. Yeah, so yeah, we were taking this d total d out. That's what we were calculating here. This is d total d out. This is d air total d out, really. The air total d out. To be consistent with my terrible naming scheme here. So now that is back propagating. Now we have H1 and H2 are back propagating to our input, and we can't back propagate to our input. So now we're done. Now we are done. Yeah. Okay, so I think we did it. 8:55, J Lido, Kylink, Papa, Big Boom, Bite Schmied, maybe? Welcome, welcome. Thanks for hanging out. Okay, so let's push this up. Git commit works with comments, right? Awesome. Now the code is up for those of you that want to poke at it. It's pretty great. So what we want to do, one target, so our input, what is our input? Do we have an input? Yeah, it's just that. Fine. Bias, I'm not clear how the bias changes. I think a bias is a static thing. I don't think he ever changes, does he? So it changes the weights, but I don't think we can change the bias. At this point, when we feed forward 0.5 and 0.1 to outputs, neurons generate 0.01 and 0.98. If you made it this far and found any errors, drop me a note. Great. Okay, so let's do that real quickly. Let's make sure that we get our that we do the next forward pass. Right. Let's also take a bunch of these logs out. I wish you could put I wish there was an easy way to put math formulas as comments, you know? You can actually like write stuff down inside of your code. It'd be super handy. So we wouldn't have all this spam everywhere. That'd be really nice. Okay, that's that, which is good. And here, E1, E total. That given target output. Right, so this error total, we don't actually use anywhere. It makes me a little nervous. Don't we use that somewhere? Apparently not. Given target. Uh-oh. Yeah, I'm doing something. I feel like I'm doing something wrong here. I mean, I'm not doing anything wrong because everything works, but it worries me a little bit that I don't understand it. That I have this code here that doesn't seem to do anything. That I can just delete willy-nilly, right? Like if I just get that out of the way. Oops. If I just get that out of the way, I still get the exact business that I care about. 2995, 2497, 1995, 1497. So I don't need this. So why do I have it? Why did we ever calculate this, right? This error given target business. This guy, the 1/2 times that guy squared. Where did that come up? Because that was a thing. I remember us talking about it. Where did we talk about it? Yeah, this guy right here. So I guess we only did that because we wanted to look at what the formula was. And I didn't actually need to calculate it because we just took its derivative and then we were happy about life. I think we only care about that guy's derivative. We don't actually care what the error is. But yeah, that's fine. That's fine. What is our error total? Is that an interesting number that maybe we'd want to show? 0.29. So if we did that, output weights, I don't care about doing that one. Forward pass before int I equals 0, I less than 2, We'll run this twice. Right? So this is our run 1. So run 1 and run 2. So we should see when he runs it the second time, I want to make sure we get the same numbers he does. Our forward propagation, we should get this guy and this guy, right? That's what we're looking for. So it's going to run 1. Our output is here. And our run 2 is just as bad. We didn't do it. A little bit better, but oh, after repeating this process 10,000 times, my goodness. The error plummets to some point. That point. Okay, so finally we've updated our weights. We feed forward 0.5.1. The error on the network was this. After the first round of propagation, the total error is now down to this, right? So that's what we care about. So error total is 21102.8. Yeah, so it is correct. It is correct. But then if we run it 10,000 times, which we're not going to do, we'll run it 200 times. Let's see what happens after 200 times. Student programmer, thank you for following, buddy. Appreciate it. All right, yeah. So now our error is much smaller, and our output is point. So instead of being 0.99, we're at 0.9, which is better than where we started, which was at what, like 0.75 basically. Now if we run it 500 times, this is fun. I'm excited about this. 500 times 0.94, yeah. So we're going to do it. We're going to sit here and we're going to watch this guy 10,000 iterations. So there's our first 1,000. Looks like it'll take about 10 seconds, 20 seconds. 2,000. It's at 0.97. I know it's too fast for y'all to drill. Well, maybe it's faster for y'all to read because it's at only like 20 frames a second. 5,000, we're halfway done, and we're at what, 0.98, if I can read that correctly. So we're getting there. 7,000, so we're 3/4 of the way there. Here we are, 10,000. Our error is 0.00035. Is that what he saw? 1, 2, 3, 4, 3, 5. Yeah, so we get the exact same error that he's getting, which is great. Great news, everyone. And we get 0.1591. He gets 2. Oh, it's probably just because it's not spitting out very nicely. I'm going to assume it's because it's not spitting out very nicely. And then 0.98, 0.984065. Yeah, I'm gonna assume. Let's stop it though. It might also be at this rate with after 10,000 iterations, there might be some rounding, some floating point error. So that's a possibility that that's what's going on, because it was pretty close. So now what this is going to get us is, there we go. So now we're at the breakpoint. So now we can look at our output, and at the outputs, this guy, and output 2. Now they're printed with a bit more accuracy, right? So 159, yeah. So it is a little off from his. I'm curious if we used double precision instead of floating point, if we would do it very much. Anyway, I'm super happy with this. Commit. 10,000 iterations gives correct result. So working network. Cool. This is awesome. This is really good. So it's 2:15 a.m. my time. What I would like to do, this is kind of like my plan for the future on this guy, is here, let's go to GitHub, because here it is. This is the code that we all just worked on. There you go. It's in the chat. You can go look at it. So you can play with it yourself if you feel like it, but let's also do a couple things, because what I would like to do is create a neural net class that handles sorting the forward back propagation calls. Class to manage a directed acyclic graph for all the neurons. Create an LSTM from these neurons. So here, now we have a really good, this is going to be a stream to-do list, right? I'm not gonna make issues for every single one, because that would be overkill. But what I would really like to do is, so in this graph right here, I still don't understand where these biases come in and how we decide what the name is, or what the value is for this bias. Maybe it's arbitrary. I don't know. Maybe we can just set it to be some random number between 0 and 1. I don't know. Excuse me. Maybe this bias can also learn with the network after we backpropagate each layer. Maybe it's maybe we can update the bias somehow so that it runs faster. Right now, it's also, it's a directed acyclic graph, right? So all of the edges point in one direction. They all always point forward. What I would like to do, let's pull this guy up again. So what we have right now is we have some neurons, right? And this guy, they always go forward, right? So what I would like to do is have something a bit crazier, where we have feedback loops in these neurons, right? And then here's our output. So that way, instead of like the standard, somebody mentioned NumPy, right? And the normal way to do this is you have neurons, and then you have these layers. Each neuron ends up being a vector, and this vector is kind of the weights for the previous layer. And so then that means this entire layer is a vector of vectors, which is a matrix. And so then you're doing matrix multiplications back and forth, right, between layers. But what I want to do is I want to create a lot messier diagrams here. And this guy, I guess you could say, like, this is one layer, and then anything that feeds into him is one layer, and then whatever feeds into him is maybe another layer. But then what happens there, right? Like, you have these two feed into this endpoint, but then this layer is also feeding into itself, which is weird. So anyway, so I want to get into that kind of stuff where you just have these bizarre connections of everything connecting to everything else. And then I want to just arbitrarily say, you right here, you're the input and you're the output, right? And then there's just a mess of just absolute gobbledygook in the middle. And then train those kinds of networks, which I think would be really fun. And the other thing we can do is there's a LSTM, which is, oops, so that's the ugliest M I've ever written in my life. That's a slightly less ugly M. There's a long-term, short-term memory neuron of sorts. So it's actually, as I've understood it, it's kind of a collection of neurons, right? So typically you have this, right? And it feeds in to something, and so it's looking at that. But here, what this single neuron can actually be modeled as like a different kind of graph, right? So the input, this here gets 2 inputs, and then it sends out 2 outputs right here. But then maybe it does some crazy stuff here, right? Something like that. Like I don't remember what the structure of it is, but it's something like that, where this is a particular formula that decides whether or not it saves value in some memory node, and then those 2 memory nodes get output. And anyway, it's something like that. But I think that would be a lot of fun to try and model with this situation as well, because this way we have we can put a UI on it, so that way every single neuron has an interface, and we can actually learn exactly how these values flow, and we can visualize the strength, the value of this weight, and the value of this weight, and the value of this weight, and how they change as we get forward and backward propagation, and what the network actually ends up kind of looking like and feeling like as values flow through it, which I think would be really, really neat. Anyways, but that my friends, is everything I have for today. But everything is up on GitHub, so check it out. Look at the code. Thank you for hanging out. I'm going to call it. Feel free to follow if you want to get an email next time I stream. And until then, enjoy it. Oh, pirate. Sorry, man, we're closing down, but thanks for joining at the very last moments. All right. Thanks, guys. Take it easy.